Hello everyone and welcome to the channel. In this video I want to improve the interaction between the main clock and the Teensy clock. I want the Teensy to be able to switch on when the user is connected to the trace. And once you have done that, I want to do a timing analysis of the clock switching circuitry to determine the fastest frequency at which we can run the fast clock. Once we found the maximum frequency, I will adapt the clock so that we don't exceed the maximum frequency. So I hope you enjoy. Okay, so there are a number of things that I want to refine on the rest of the CPU. And the first and more important one, I guess, is I want to improve my development workflow. For now, each time I want to program the EEPROM, I have to put it out, put it in the programmer, program it, and then put it back. And we have a Teensy here that we use for the monitor, but it's a bit janky, it doesn't really work very well. So I want to improve this development workflow, and this is going to be centered on the Teensy. I want to use the Teensy as an EEPROM programmer, but I also want to use the Teensy to control the CPU. For example, to do single stepping of instruction, to be able to set breakpoints, and to be able to read and write memory. Basically to work like a debugger interface. But for that, we need more I/O pins, and all the I/O pins are currently occupied, but we can solder in a header here. We have 8 additional I/O pins that are accessible here via a header. So I want to do that today. And the first use of these new pins that I will implement today is I want to remove this switch in the clock here that I'm currently using to switch the slow clock from the built-in clock that is here to the clock generated by the Teensy. The way I want to do it instead is I want a control signals from the Teensy that can disable this clock module when I'm using the debugger. So anytime I'm connected to the debugger, this clock will be disabled and the Teensy will take over. But if I'm not connected to the debugger, the Teensy will not tri-state this clock, and I can use the manual interface to work. And so I think that's going to be a better way of designing it. But we do need an additional control line on the Teensy, and so I need to solder that header now. So let me pull out the Teensy from the circuit. There we go. And you can see here the 8-pin header that I'm going to solder. Okay, and so I've made a little 2x4 female connector going to a 1x8 coupon cable in order to connect to this. So let's plug it back in. And I'm going to be removing this jumper. It is the lower byte of the address, and I'm connecting it directly to the new header. There we go. And now we have 8 new control lines available. So let's go and update the monitor code to check that we haven't broken anything. When I turn on the power, and we still have our hello world message appearing. So at least that's good. Let's go into Arduino. And we have to change the low byte of the address from pin D to pin A. And yeah, it looks like we're still reading our addresses correctly. So let's go ahead and add the new ports for port A to our schematic here. And we can take a look at the footprint I'm using for the Teensy to get the pin numbers. As you can see here, the pins go from 44 to 51. There we go. And so we have connected the address pins. And for now, nothing is connected to port D. Now, I said I wanted to be able to control the clock from the Teensy, and if we go to the clock, at the moment, this is a manual switch, which when activated switches from clock of the Teensy to the slow clock and vice versa. In order to be able to switch the clock programmatically, I want to tri-state this output here based on a control signal. And then we can connect the clock in pin to the output of the monitor clock and have the monitor clock output the clock in instead. So in order to do that, I need to replace this 74AC151 by a 251. And unfortunately, this chip is not available in the AC family. So we'll have to use a HC chip. However, that means that we can remove those current limiting resistors because HC chips are going to have less powerful outputs. And so I think we're fine to go with that. But the difference between the 151 and the 251 is the 251 has an output enable signal, which means that the output can be tri-stated. And so if we connect to this a control signal coming from the Teensy, let's call that clock enable, and it's going to be active low. When this is low, then the clock is going to come from our main clock. And when it is high, the Teensy can drive the clock. So we can remove this switch here. And instead of monitor clock as an input, we have our clock enable signal. So on the monitor side, we have clock enable that we need to generate. And that's an output of the Teensy. And then we also have the clock in. And this is going to be bidirectional. It's either driven by the main clock or by the Teensy itself. So I'll keep the clock in connected to the same pin because we want to be able to use interrupts for it. And the clock enable, I'm going to connect to D6 because this pin also controls the LED that's built in on the board. And so that's really useful because when the main clock is active, this is going low and the LED is not turned on. But when the Teensy is driving the clock, then this is going to go high and we're going to see the LED. So we'll be able to see who is driving the clock just by looking at the LED on the Teensy board. So let me connect these at the top level. And there we go. We have to make a number of updates to our monitoring program. First of all, the address pins. Then we have clock in, which is still in 18, but we also have clock enable, which is on pin 6. So by default, at boot up, the default state is going to be the main clock is active. So we want to disable this pin. We can turn it into an input. And then clock en is an output. And we can initialize it to 0 so that the main clock is active. So I'm just realizing we're not initializing all the address properly here. Okay. And then what we can do here in the loop is we can check if the serial connection is active. And this only works on Teensy because Arduino boards always return true. So if the serial connection is active, then this means that the serial monitor has been opened by the user. And so we are looking at the serial monitor. And so at this point, we want the Teensy to be driving the clock. So we need to disable the main clock so that the Teensy is driving the clock. And then we can do our writes to the clock in. And it's not inverted anymore, so we can revert that. And basically we can do all of this only when the serial connection is active. And when the serial connection is not active, we want to revert to the main clock. And so we can do this. And of course, we also have to change the pin mode to be input so that we don't have a conflict. And here we need to change it to output. Okay, so let's try this out. Okay, so I have here a 74HC251. Let's install it on the clock. And I will remove these resistors. There we go. So this shouldn't have broken anything. Yep, still works. Okay, so then I can remove this switch here. There we go. And then this is the signal coming from the Teensy. It's currently connected to the clock in pin. So I will get clock in from here instead. And then we need clock enable. And clock enable is on pin 7 here. So we need to remove this jumper to ground. And we can connect that directly to the Teensy. And actually I should probably add a pull-up to this pin. If there's an issue with the Teensy that it is not driving the clock enable, we don't risk creating a conflict where both of them are driving the pin at the same time, just as a safety. So for that, I'll just use a 10K resistor to VCC. Okay, so if I turn on the power now, this is currently configured as an input, and so it's not going to be driven, and so the clock is going to be disabled. As you can see, it's not going through to the CPU. So let's program the Teensy now. Okay, so the serial monitor is not open at the moment. But if I go and open it, you'll see that the clock speeds up a lot. And that's because it goes to the Teensy. And as you can see, the LED on the Teensy is turned on. That means that it's currently driving the clock. And I can reset the CPU and get the values before it stops. Okay, and if I close the plotter, then it goes back to the built-in clock. That's awesome. Okay, so one thing we haven't really analyzed so far in the clock circuit is the timing of the clock switching. If we look at the fast and slow selection bit, for example, we know that the slow clock is going to have a falling edge here. And because the slow clock is orders of magnitude slower than the fast clock, we know that the slow clock is going to stay low for at least a few fast clock transitions. And so we can assume it's going to stay constant for our analysis. But let's say we have a fast clock falling edge here. This will translate to a change in value in the fast and slow signal, which will go as an input to the multiplexer here. And then this will result in a change of the clock signal. In order for this circuit to stay consistent and to not shorten the fast clock cycle, we need the switch here at the multiplexer to happen before the fast clock has a rising edge. So we want the switch to happen while the fast clock is low, because if the switch hasn't happened when the fast clock has a rising edge, it means that we have shortened the period of the fast clock, and that's not good because the fast clock is intended to be the maximum speed that the CPU can run at. So we don't want to shorten its cycle. So we have the fast clock falling edge. This takes some time, some nanoseconds. Then this goes to the fast and slow signal. This takes some time. And this goes to the clock. So what are those timings? Well, for the fast-slow selection bit, we can look at the datasheet of the 74HC112 JK flip-flop. And we can see in the switching characteristics that the propagation delay of its clock input to its output at 5 volts is going to be a maximum of 31 nanoseconds. So over here, this is 31 nanoseconds. Then the propagation delay of the fast and slow selection bit to the clock is going to be governed by the 74HC251. And if you look at its datasheet in the switching characteristics, we can see that the propagation delay of the selection bit to its output is going to be a maximum of 51 nanoseconds. So over here, we have 51 nanoseconds, and that's the 74HC251. So all in all, this means that the minimum half period of the fast clock must be lower than 31 plus 51 nanoseconds, which is 42, which means that the maximum frequency of the fast clock is 1/82, 1000/82, and that's 6.09 megahertz. So there is another chain that we have to take into account, and that's the chain going from the fast clock here to the run clock, to the pulse run signal, and then to the multiplexer. So let me copy this. And so the fast clock is going to have a falling edge. This is going to take some time at the 74HC151 to be propagated to the run clock. And then the run clock is going to take some time going through the 74HC112 to go to the pulse run signal. And for this, it's going to be 31 nanoseconds as well. And then the multiplexer takes the same amount of time. So if we look at the datasheet of the 74HC151, we see that the propagation delay of its input to the output is going to be a maximum of 49 nanoseconds. So similarly, we want the selection to happen before the fast clock has a rising edge, which means that the minimum half period of the fast clock is 49 plus 31 plus 51. That's 139 nanoseconds. And so the maximum frequency of the fast clock is 3.81 megahertz. So as you can see, we can't actually run the fast clock very fast with this circuit, and it's even lower than 4 megahertz, which is our target. So the way that we can improve this is to go to faster chips. So unfortunately, the 74HC251 is not available in a faster family, at least in DIP format. You can get a 74HC251 in SMD, but I'm trying to use only through-hole chips here. But the 74HC112 and the 74HC151 are both available in the AC family. So let's see what happens if we switch both of these to AC. Let's start by switching the run clock here to AC. So if you look at the datasheets for the 74HC151, we see that in the switching characteristics from the input to the output, it's going to be a maximum of 13.5 nanoseconds. So we can update this one, 13.5. And so this brings the maximum frequency of the fast clock to 5.23 megahertz. And similarly, if we replace this chip with an AC112, we can see in the switching characteristics that the propagation delay from its clock input to its output is going to be a maximum of 9.4 nanoseconds. And so we can update our calculation here. So this brings the maximum frequency of the fast clock to 6.76 megahertz. And we can do the same for the fast and slow bit by just inverting this one with the AC version. Okay, so overall, maximum frequency of the fast clock is 6.76 megahertz. And I've added here the frequency of the fast clock depending on the divider settings. And so you can see that it works for all of them except the first one. We can't actually run the circuit at 10 megahertz. Okay, so I need to update the fast clock so that running it at 10 megahertz is not possible. There are two ways I could go about that. I could update the frequency of the oscillator to a lower frequency so that when the divider is set to 0, we are below our maximum frequency. However, the first step of the divider is a division by 2, which I think is pretty big and I would like to avoid. So what I can do instead is add 1 to the divider setting. This way, the first setting is going to be 5 megahertz and the second one is going to be 3.33, which I think are two good values for my computer. The first one is a slight overclocking, which might be useful to have, and the second one is a safe frequency, given that our maximum goal is 4 megahertz. So this is going to be a bit overkill, I guess, but I will use an adder chip to add 1 to the divider setting. The other thing I'm noticing here is that the values with the most significant bits of the divider set are not really useful. As you can see, the intervals between each frequency here is very small, and so it's not really useful. I'm going to fix the most significant bits to 0 and switch to a 3-bit dip switch. And we're going to ignore all those frequencies here. So let's do that. So for the adder chip, I'm going to use a 74HC283. It's a 4-bit adder. And we can ignore the carry input and output. So I will connect the carry input to VCC, and this is going to be our adding by 1. And then I'll connect all of the second bits to 0. As well as the most significant bit of the first nibble. Remember, we want to ignore all the values where it is set. So we can remove this section here and switch to a 3-bit dip switch. There we go. Okay, so first of all, I will replace the 74HC151 here with the 74AC151. Then we can replace the two JK flip-flops, so the 74HC112 with the AC version. There we go. And the clock is still working. And I have here a 74HC283, which I'm going to put here in order to compute the dip switch. And I have a 3-bit dip switch here. Unfortunately, it doesn't really want to stay in the breadboard properly, so I'm just going to use a socket that I know is going to stay in place. So I'm going to put the 4-bit adder over here where the oscillator is, and I'm going to move the oscillator down here. Let's get started. Okay, so we need to connect pin 7 to VCC. And then we need to connect pin 2 and pin 6 to ground. And then 11, 12, and 15. Pin 4 of the dip switch goes to pin 5 of the counter. Pin 5 of the dip switch goes to pin 3 of the counter. Pin 6 of the dip switch goes to pin 14 of the adder. There we go. Then pin 1 goes to pin 1 of the counter. Pin 4 of the adder goes to pin 15 of the counter. Pin 13 of the adder goes to pin 10 of the counter. And pin 10 of the adder goes to pin 9 of the counter. There we go. This should be everything. Let's try it on. So it looks like the clock is still working. Let me bring in my oscilloscope just to check the values. Okay, so when everything is at 0, it's 5 megahertz. 1 is 3.33, that's correct. 2 is 2.5. 3 is 2 megahertz. Then we go to 1.67, 143, 125, and 111. Awesome. So this is all still working. And I'll go back to 3.33 megahertz, which is the safe frequency here. Okay, so I'm pretty pleased with the progress that we made in this video. We did a bunch of work on the Teensy monitor. We've added this new header so that we can access new GPIO pins. And we made the first use of these new GPIO pins by controlling the clock output from the Teensy and being able to enable and disable the built-in clock when the Teensy is driving the CPU, and we're monitoring it through the serial monitor. Then we put some finishing touches on the clock. We never computed before the maximum frequency that is safe for our switching circuits, and so we made sure to update our switching circuits and cap our maximum frequency based on those results. And so the maximum frequency that the clock can now run at is 5 megahertz, which is a bit of an overclock on the acceptable speed of the CPU, but I think that is fine. And we have the 3.33 megahertz frequency that is safe for the computer. So that's really cool. In the next video, we'll add the keyboard interface that I'm going to port from my Venator 6502 to this computer. And so this is going to allow us to enter commands and text and have them displayed on the LCD. So that's going to be pretty exciting. I'm also going to continue progressively working on putting finishing touches in all the circuits to get ready for PCBs. So stay tuned for that next video. In the meantime, if you have any questions or feedback about this video, please let me know in the comments, and I hope to see you in the next one. Goodbye.